go with our traditional opening.
Are there any questions?
Yeah, I had a question. It was like one of the questions on the pre-lab. It was fine. You were using the static and kinetic friction, like we had an amount for that.
Right.
We could tell what the acceleration of the box was and what kind of friction was acting on that box. Can you maybe explain that or do a problem like that?
I mean, I could pretty much do box on ramp.
I think that's what it was on the pre-lab.
So first off, when you're dealing with these type of problems where there is friction involved and it's starting at rest, back it up slightly. If it's not starting at rest, if it's already moving, then we don't have to worry about is it moving or not. If it is moving, then we're going to be using kinetic friction. If it's not moving, we have to decide, is it going to be using kinetic friction or not? So, mass is pretty much irrelevant, I believe, so but we'll go for 5 kilograms because I have no imagination right now. Make this 0.8, and use of K is 0.3, and we'll make that 53 degrees. So force diagram. I know that if it is going to accelerate, it's going to accelerate down the ramp. So acceleration would be in that direction. So then we have to then we set up a coordinate system. I hat and then J hat. So that's force diagram, direction of acceleration, coordinate axes, decomposition phase. Well, let me just quiz you. Does anything need to be decomposed? Yep, because it is not in either of those positive or negative directions. And we've broken up many times. This would be W sine theta, W cosine theta, normal force, friction. Equations of motion.
I hat would be W sine theta minus F for friction equals MA. And then J hat would be W cosine theta. Y minus, or Y is equal to W cosine theta.
I'm going to stick to the pattern first, but ultimately what you said is correct.
Okay.
And then we bring the W cosine theta instead of here. Oops, spoiler, equals 0. By the way, on the lab, when the question is what is the theoretical normal force, well, the theoretical normal force is equal to W cosine theta. The theoretical force down the ramp, we're sort of working on the assumption in the lab that it was frictionless. It should have been low friction, but we're working under the assumption that it's frictionless, and therefore that would go away in the lab in the theoretical part, and so the theoretical force to keep the ramp from going down, to keep the cart from going down the ramp would be that. So that's the theoretical force, theoretical normal force. I guess theoretical net force. Although ideal might have been a better word than theoretical, but I'm probably not going to change it. All right, so then comes the substitution phase. What do we have an independent formula for?
W.
W equals mg.
Thank you. And so I've got mg here, so mg there. And this is the point here where we don't know what the friction is. Is it static or is it kinetic?
So for F, do we plug in the 0.8, or would we use 0.3?
For F, I don't know if there's more in your head than what you said, but based on what you said, no, neither. Because friction is not that, those are not the frictions. Way too many times I've seen that mistake. These are coefficients. They are no unit whatsoever. Friction, kinetic, equals mu sub k times the normal force. And F sub s is less than mu sub s times the normal force. Since we don't know if it's moving or not, the first proper step is let's determine if it's going to move or not. So let's figure out what the static maximum, let's figure out what the acceleration would be if maximum static were at play. Because the static friction is going to be, we have a huge range here from 0 up to this, or based upon some students' labs in the past, a negative value, but let's assume not. The static friction is from 0 up to this, and we don't know where it is, so we really have only two choices. We can only plug in the extremes, and it makes sense if we're testing it to plug in that extreme. So it becomes mg sine theta is equal to, oops, not equal to, minus u sub s times y, which is mg cosine theta, is equal to ma. And this is what we're solving. And if you want to plug in the mass, that's fine. Mass does not matter here, because every term has mass as a factor. So we're left with 9.8. You know what, for the sake of this, let's put it on Earth too. Sine of 53 degrees, about 0.8. So this becomes 8 minus 0.8 times g cosine theta, which should be about 6, is equal to the acceleration. So we end up with 8 minus 4.8, which is 3.2 meters per second squared. Because we have a positive number with static friction, well, we know the acceleration is going to be down the ramp. We can just imagine we've put things on ramps, I'm sure, at some point, and we see them slide. If you've ever been to a playground and been on a slide, you've demonstrated this with your own person. Because this is positive, we know it's going to move, and therefore we would use kinetic. So that 0.8 would then change. To 0.3, that 4.8 now becomes 1.8. Yeah, we're doing the math right. So the acceleration is 6.2 meters per second squared. Dramatic pause for questions before, I'm going to change it slightly. You agree?
Okay, so you started off assuming mu sub s,
Yep.
right? And so, just trying to figure out, cause like, for my like my y, cause I already had my y value and I already had my like, my two components.
Mm-hmm.
So, I just got a negative 0.8 as my answer for the first one.
Using these numbers? Or using the, I just made these numbers up. This is not specific numbers to.
Oh. Yeah, never mind.
Okay. Other questions at the moment?
you're going to solve for, so when it asks like, what is the friction force acting, you would then plug in what to find, because the friction force would be friction kinetic, because it's moving.
Yes.
In this case.
Yep.
And so then you'd plug in the friction kinetic and then the Y value,
Yes,
and then that's your friction force.
yes. So the kinetic friction in this case is u sub k times mg cosine theta, which would be 0.3 times 5 times 10 times 0.5. No, wrong one. Times 0.6. Whatever that is. 9? No. Yes. So that's the friction acting. That's the acceleration.
How did we get Fk equals mu sub k mg cosine theta?
I know that the kinetic friction is equal to mu k times the normal force.
Yes.
You yourself said normal force is equal to mg cosine theta. That's where it comes from. Mu k mg cosine theta. Did I misunderstand the question?
No, I got it.
Okay.
And if you plug in for mu sub s, and you get a negative number.
All right, so let's do that. Other questions on this before we change it? Just make Ibrahim happy. Before you get a swelled head, I was gonna do this anyway.
Yeah. This is,
Notice that whatever friction that we pick doesn't change our force diagram here. Let's make this extreme. If I actually write something, 1.6. And I think I mentioned it before, mu sub s is rarely over 1. It is possible, and I have seen some combination which gets that, but that would be incredibly rare. So the first thing you go through is, again, assume maximum static friction. So put a 1.6 in there. And so now that becomes 9.6, so we get negative 1.6 meters per second squared. If this is a legitimate answer, we have it starting at rest, it accelerates in the negative direction, which means that I put this on the ramp and it started accelerating up the ramp, which is not going to happen. And because that's not going to happen, it does not move. Therefore, the acceleration is not negative 1.6, the acceleration is 0 meters per second squared.
it's not gonna go back off the ramp.
If you can somehow manage that,
We're going to Vegas.
oh, we're buying Vegas. Now, 0 meters per second squared. So the question is, what is the friction? The friction is not, well, multiply times 5 as I factor the mass out. But the force down the ramp is 40 newtons. The normal force is, if I can do math now, 30 newtons, yeah, that's right. My friction, it's starting at rest, it's gonna stay at rest. The net force has to be 0. So the friction force is not 5 times that. The friction force has to be 40 newtons because the acceleration is 0. There were a couple of pre-labs where people put down that value, ignoring the fact that it's not going to move, therefore the static friction is only whatever it needs in order to keep it from moving. questions? All right,
Can you, what, did you do this in class or was this from previously?
that's the sausage. Does that look like my handwriting?
No, that's not.
That is way too neat. However, I would quibble. You know, sometimes the OCD kicks in.
Is that physics 251 or?
No, that's 151, that's the 8-week course.
Oh.
Two-dimensional collisions.
Okay.
We'll get there. Other questions? Only get to use these old ones that I printed out and never used. Put that stuff away. So, if the road is frictionless, at what speed should the car go so that it does not slide up or down the ramp or the bank?
0.
You put an object on going 0 meters per second on a frictionless, I guess at that point, if you call it a ramp, it won't slide. Wow. I've been lied to.
Well, that I'll be gonna be rich.
The Drake. All right, so what's the first step?
Force diagram.
Yes. All we really care about is the car here. All right, what are the forces acting on it?
Forgot the wheels.
There's the, oh wait, first.
There is normal force.
There's friction acting up the ramp. Oh,
It says frictionless,
Oh, it
even
does
if,
say- okay.
it might not look like it,
Sorry.
but it's supposed to say frictionless.
okay, so no friction.
So,
Is that it?
well, we don't know if we decompose it yet, but I think that's all.
Okay, that is indeed all. All right, so there's the force. Acceleration, what is the direction of acceleration? And I will say this is the point where the big mistake happens, for those who make the mistake.
Go for it.
And that is the mistake.
Go.
Thanks for demonstrating.
What did he say?
It's not, it's,
Would it, if we're looking behind the car and
Yeah.
we wanted to not slide this way, that would just forward?
There would be no acceleration.
There.
Wait, hold on.
When you have an object that is traveling the car is traveling around like this.
Oh, okay.
Yeah. Right, done the overhead.
So it's a racetrack.
Oh.
For cars traveling in a circle, or even on a curve, it doesn't really matter what's happening out here. I mean, it could go, the road could go like that. All we're concerned about is at this moment where there's a curve in the road, the velocity is changing because of changing direction. So, the acceleration is always towards the center of the circle, which is that way, or over here, that way. That is the acceleration, direction of acceleration. Therefore, what coordinate system should we set up?
J hat going up, and then I hat to the right.
Well, can't we do J hat going in the same direction, or I hat going in the same direction as, oh, does it have to be 90 degrees?
A hat and J hat
Yeah.
should be 90 degrees.
Got it,
That's a whole nother set of math. We're gonna start getting into coordinate systems that are not orthogonal.
okay. Got it.
So when you're a college senior, physics major, that's what you do with it. Never say never. All right, so we have our coordinate system set up. Indeed, this is probably the most efficient. If you wanted to set it up so that it was like that, or if you're really a masochist, set it up so that they're not perpendicular to each other. Just enjoy it. All right, so we did A, we did the coordinate axes. What's next?
Decomposition,
Do we have to decompose anything?
2 things.
What's 2 things?
Oh no, just one thing,
What is the one thing?
Y thing.
Yeah, that's what we're breaking up this time. Unlike the box on ramp,